Good afternoon, good evening, good morning to some. Thank you for attending 5 Steps to Manage Springback and Compensation, hosted by Cimatron. Let's meet the team that's responsible for our presentation today. Ralph Picklow is our Director of Sales for the Americas for Cimatron. Mason Keju is the Regional Sales Representative Eastern U.S. David Lindemans, our Senior Application Engineer. He'll be performing the demonstration for you today. And I'm your host, Dan Marinac. I'm the Product Strategy Manager here at Cimatron. Let's just take a second to introduce you to Cimatron. We are CAD/CAM for tooling, founded in 1982 with more than 42,000 licenses worldwide. Cimatron is a comprehensive CAD/CAM solution for the mold, tool, and die makers. We offer Cimatron Mold, Cimatron Die, and Cimatron CAM individually and properly packaged for you to do your work in the industry. Additionally, we offer Cimatron CAD. It's a full 3D parametric hybrid modeling system. We have Cimatron Electrode, a specialized application just for electrode extraction, burning, toolpath creation, and Cimatron CAD/CAM, the full seat that offers all of the capabilities we've spoken about here. Cimatron Die in particular is what we're going to talk about today. It's a dedicated solution for die makers. It has quoting estimating for both progressive, transfer, tandem, and line dies. It has an FEA-based blank shape development and forming feasibility analysis. It's a dedicated design tool to develop all of your stations in your operations: draw, form, flange, trim, gut, notch, punch, pierce, etc. It has strip design with material optimization applications. There is an FEA-based springback analysis with high-quality morphing for compensation. Smart catalogs are available for die sets and components. You can validate your design with measurement, 3D explicit simulation analysis. That's an additional package from Altair Engineering called InspireForm. Collision detection tools, and FEA and ECO analysis. You can create and reuse your drawing templates incorporating customer specifications using dynamic multiple shaded views. We understand the toolmakers' challenges. Many of our employees are toolmakers themselves. That helps us understand exactly where you're coming from. We understand the need to reduce delivery time, improve your tool quality, reduce your costs, and increase your productivity. As mentioned before, Cimatron's a connected, dedicated software for design and production of molds, tools, and dies. It automates the design and manufacturing of tools to produce final parts quickly and accurately. The estimating portion will be shown in a future webinar. We've already done part 1 of this series on design. You can come to our website to look that up if you'd like to watch it again or watch it for the first time. And we covered manufacturing at that time. We're going to be focusing today on springback and compensation. Specifically, the 5 steps to manage springback and compensation. Step 1, understand your material properties. Step 2, an FEA-based stamping simulation. Make sure you understand what you're forming. Then you move to an FEA-based springback analysis. Generate your deformed point cloud, and now compensate that using surface morphing technology to reflect and imprint the compensated data into your either thin sheet part or right into the die faces if you prefer. I'm going to start though by boring everybody to tears, and I'll apologize now, but if we don't cover some stamping theory, I don't think you'll be with me through the presentation. Springback compensation is one of the greatest challenges in the automotive industry. Parts stamped from Gen 2 and Gen 3 steels are more prone to springback than parts made from conventional steel. Many of us have our experience in conventional or high-strength steels. These Gen 2s and Gen 3s are creating some problems with springback compensation. Verification of springback and springback compensation is now common practice. Compensation of the die faces is implemented in the opposite direction of springback while applying a percentage of the value. Computation of the compensation value can be carried out with morphing. The compensated tool geometry can automatically be used as input for the next simulation. With very few iteration loops, a final stamping can be achieved within the required tolerances. I want to take a moment now to identify the references for the source material you're seeing on the theory here. The World Auto Steel Group with the Advanced High Strength Steel Insights.org is their website. They offer a free Advanced High Strength Steel application guidelines PDF. You just need to click on this link to get this, and you are welcome to it. They offer it free of charge. Also, the Auto Steel Partnership is a fantastic group. I encourage you all to attend their free webinars, which will teach you many of the aspects of not only about steel production, forming of steels, forming of parts for the body and white world, but also the joinery of those, if that's part of your business practice as well. And I'd be remiss not to note that Dr. Danny Schaeffler from Engineering Quality Solutions is a main contributor to all of these groups, and some of his materials referenced here as well. Let's start with material properties. Basically, we can look at, depending on where you are in the world, 3 different coupons of steel that would be taken from the sample that you want to work with. There's the ASTM, or the American sample. There's the DIN standard for Germany/Europe, and the JIS standard, which is the Japanese standard. All just a little bit different, but at the end of the day, they do the same thing. You put the bottom of the coupon in a gripper, you pull it on a Ingstrom type machine with a force, and you give it a pull. And basically from that, we can determine the stress, which is the force applied over the cross-sectional area that we're working with. The material properties we're seeking specifically for springback are the elastic modulus, E. It's the main contributor to this. Yield strength, ultimate tensile strength, N value and R value all play a major role in the formability of the part, which induces the strains on the part, but springback is the releasing of those strains, and it's incredibly important to the process. So once we put it into a machine, we can then measure on a plot what the extension is of this sample against what the load is, or the force is, that we're applying. We take that extension load diagram and we can convert it very easily into an engineering stress strain diagram. What's important on the stress strain diagram, and I'll use engineering stress and engineering strain here as opposed to true strain, which I'll get into in a minute, is that I think we've all pushed on the side of, let's say, on the side of a pop can and let it crinkle back and forth. When it bounces all the way out, you're in the elastic portion of the curve. Once you've pushed on that side of a pop can or a soda can so hard that it stays deformed, you've now entered the plastic portion of the curve. So as you're pressing on a curve, it can return to its shape if it stays in the elastic zone. Once you've crossed the yield strength of the material, it starts to stay deformed up until the ultimate tensile strength, at which case it's achieved its maximum. And then depending on the necking availability of the steel that you're working with, it will hang around until it finally breaks at total elongation. So the important aspects on this plot are: we determine the elastic modulus by measuring the slope. of the elastic portion of this curve. The yield strength is this point where it breaks between elastic and plastic portions on the stress strain curve. So that's your yield strength. The ultimate tensile strength, or just tensile strength, is the maximum strength that that material can achieve. When we strain a material all the way up the curve and all the way up to here, if we let go at that point, or we stop stamping the piece at that point, it will return and fall back in a line parallel to the slope, the elastic modulus, and it will fall back down to here. This distance here will be the amount of spring back you achieve. So if you try to get a spring back calculation while you're in the elastic zone, it'll return to its original state. Once you've cleared yield strength, at some point along this curve, you will come back and get different spring back amounts depending on how much you've strained the material. Let's take an example of this. If I was to put a circle grid over a blank and put it into a tryout press and stamp it, I would get a bunch of circles that would look something like this. If I take circle A at 0.2, doesn't really matter your units, but let's work with 200 thou diameter circle that I started with on the blank. If after stretching I measured it to be 280 by 230, then I can quickly calculate the strain and get the major strain at 40%, because that's the major axis of the ellipse that circle stretched to. If I look at the minor strain, I look at the minor axis of the ellipse that circle stretched to, and I would get the minor strain. So if I get a major strain of plus 40 and a minor strain of plus 15, I could look at a second circle on the part, again, 200 thou. Here I came in at 256 and 170, so I now get a major strain of plus 28% and a minor strain of minus 15% because it actually shrunk in the minor direction. So we take those points, A and B, and we plot them on a major strain on the vertical axis, minor strain on the horizontal axis, and we plot them. This is referred to as the strain ratio, which, depending on what the ratio becomes, we get into different zones of modes of deformation. Stay with me, it gets a little theoretical, but it's important. If we now look at plotting these points, we can then calculate according to Goodwin theory and Keeler theory. So this is the Goodwin-Keeler diagram, or what's commonly known as the forming limit diagram, or FLD. Points plotted that plot above the forming limit curve fail. Your part will split. If you are below that and above these two lines, you're into a safe zone for how you form the material. So basically, if we look at draws, any piece that you're drawing will have a set of circles, the initial circle diagram that I showed, and the ellipse that it forms to will be a draw, a plane strain, or a stretch condition. And depending on where your point plots on the FLD, you'll understand fully whether you're in a draw, stretch, or plane strain condition. It gets a little more complicated than that when we throw up the full modes of failure on a forming limit diagram. Here you can see we've actually given names to various axes. We'll start off with minor strain, major strain, just like we did before. We have the forming limit curve, which depicts the material properties. We then apply a 10% margin of safety onto that forming limit curve to make sure we're good. You'll notice points that come above this should be plotted red. Points in this marginal band should be yellow, indicating marginal. Now, we have 5 modes of deformation: equal biaxial stretch, plane strain, uniaxial tension, pure shear, and uniaxial compression. And we will color points plotted in these areas for you as purple, dark gray, light gray, green, red, or yellow. And this is what's commonly known as the first mode of failure, because that means you've stressed the part past its abilities as a material to be stretched. The second mode of failure could come into play if you apply a thinning limit onto your curve. And any points plotted past your thinning limit, if the material has a thinning limit, would then go into an orange color. There is also a shear limit for the third mode of failure, where if the material can only sustain so much shear, it would get plotted another color. No one needs to memorize this. You just need to understand what the colors mean. So I tend to put my left hand over the diagram, and I can see that equal biaxial comes out along my thumb, plane strain on the index finger, uniaxial tension on the middle finger, pure shear along my ring finger, and uniaxial compression along my pinky. So these are the 5 modes of deformation, and it's important when you look at a forming limit diagram to know where the points are plotted, because that helps you with the countermeasure. Now, I promise not to get into too much theory, but I think I need to get into springback. So when we look at springback, we look at the stress-strain curve. You can see the elastic portion and the slope, which is E, right here. And you can see with the lower strength steel, it will move all the way up to here, and the springback will come down and be the distance between B and C. You can see on a higher strength material that it goes up much higher and continues up to here, and its springback is much larger than the lower strength steel. And this is why, even though steel is steel and the elastic modulus is the same. If we now throw a wild card into it, like aluminum, you can see aluminum has a completely different slope and Young's modulus. You can also see that its springback is at least 3 times what you would get with steel. And it's significant to note this, because if you try to change your designs from steel to aluminum, especially with the advent of electric vehicles demanding aluminum and lighter weight materials these days, realize that you're going to have a much larger issue with springback. So, simple springback. If we take just a simple bend over a radius, we see that we can only induce so much force, but after we've induced it, depending on the material, it will spring back to this yellow state right here. So what can we do in the design to change or to control springback? First of all, if we're dealing with a rail section, perhaps we should try to get the designers to actually put some angled walls into place. This will allow for easier overbending to control the springback. Or we often have to make an upper and lower component if we are going to join 2 channels together and perhaps weld them or bolt them along here. Or maybe it's 2 different materials, an aluminum and a steel being riveted together over a long member here. Changing the design of the cross section from a closed box section to an angled one allows you to reduce the springback problems. So if these are design alternatives you can push back to your customer, they're often a good idea to look at. What if we add an extra forming operation? Here we can look at a part that's going through an initial crown. The crown remains. We add some flanges to pull it down. But in this case, we could actually put a negative crown in to handle the bubble out that would happen on the bottom. And you can see that the material's being forced out into the corners. And we have a problem with the inside, the sharp inside corners. So this is a schematic of how flattening a crown corrects angular springback. We can also look at 2 stages. What if we take a multi-stage approach to this, a 2-stage forming procedure for the dimensional consistency? Here we can look at a part after the first stage, and a gull wing is formed. Typically it looks like a gull wing because it looks like a seagull flying away from us while we're on the beach here over the summer. The part after the second stage could wipe those walls back down to produce a 90-degree cross-section after the second stage. The expense here is that you've added an extra stage to get there, but this is often done in the die process. A very easy way to do it is to either add some other kind of geometric feature like a step flange, where you kick out one of the walls or recess one of the walls, depending on which one's your control surface. You can add a stiffening dart, or a bird's beak as it's often called in the industry, or we can look at lock beads to lock in, or flanges to lock in the stiffness into the part. Here's an example of a B-pillar with a stiffening dart added in these two corners here. The yellow arrows will direct your eye to what I'm trying to point to if you can't follow the mouse. Here's a look at a step flange that locks in the elastic stresses on a draw wall. Draw walls tend to get a lot of wrinkling on them and have big springback issues anyway, so adding this step flange starts to lock in these elastic stresses and gets you past yield strength up into the upper portion of that stress strain curve. Other design changes you can look at. Here's a typical hat section, but you can see that the angular sidewall curl is less pronounced on the left side. Why? Because we put these vertical beads in. These vertical beads allow the wall to be stiffened and give greater support to the wall in between. Whereas when we didn't do it on the other side, you can see what kind of springback mess you're dealing with on this side. You not only get sidewall curl, but you get a big springback coming into play here. Here's an example, again, from the AHSS handbook, where a DP660 front rail upper reinforcement had to have these vertical beads added in order to stiffen the part and remove the springback. Once you're into a DP600, you're into a Gen 2 steel, you're having quite a bit of problems with springback on these parts. Common way to do this, especially in progressive die parts, is to add a rotary bending station in. And you put a rotobender in like this, and you can overbend a part, and after a few iterations, eventually figure out on the floor exactly where this part will spring back to. You should be able to lock it in with the rotary bender. Another way of doing it is overforming. If you overform and apply extra pressure at this point here on the flange steel and allow some back relief on the lower die, you can squeeze this material into place to hold this. Now it'll allow for some thickness variances through this radius, but it's another way to hold this wall. You'll know best where the GD&T holds the part to as you go through it. Some countermeasures that are a little more advanced, and I thought I'd just take a few minutes to go through these fairly quickly, is getting into draw beads and stake beads. Now we're using the press action and the forming action to control springback because the part design's locked in. We look at a dual phase 590 B pillar here with draw beads. The draw beads are down here in blue and along the walls in blue. And draw beads, I'm sure you're all familiar with them as good design engineers. However, those of you who are not that familiar with it, it's just like a speed bump in the parking lot. Why do we put these speed bumps there? To slow you down so you don't race through a parking lot. That's what we're doing with the material flow. We are stopping the material we are slowing the material down from entering to this area here and letting it stretch more. It tends to take wrinkles out because you'll have strong wrinkling in these areas here if you don't add these draw beads. Stake beads, though, and draw beads go on the blank holder. Stake beads instead go on the punch face. And if you put a bead on the punch face, you're reducing the size of the blank you need, because usually your blank has to go out and cover the punch opening line. So to work with a smaller blank means reducing costs, both for you and your customer. So stake beads are something that's coming more and more into the norm these days. And you can see the stake bead being applied on this part as we go through these areas on this B pillar. This area in green would denote the actual trim line of the part. Everything else is the extra surfacing and extra material we had to add in order to get that part to proper shape. We look at a stake bead that's machined into this punch of a DP780 material. So here you can see that these these pockets have been machined right onto the punch. Very important because it allows for a slightly smaller blank than you would have when you're working with a blank holder and a binder, and there is no blank holder on this component. So here's a comparison of two dual-face parts. We've got a 450 and a 750. You can see the 750 is just going absolutely crazy up top when it's not controlled. But if we add a stake bead in, you can see that we can control quite a bit how much that spring back is. There's still some spring back. You can still see a little sidewall curl, but it's much better than it was in the one up above. So this is the same part at different angles being shown here. There is another new hybrid method coming out that's been analyzed. And again, you can get all the details on these at Advanced High Strength Steel Insights. A hybrid bead has now appeared, which is also known as a stringer bead. And the stringer bead has a bit of a wave in it. It's not a full double draw bead, and so it works a little differently and doesn't take as much space as a double draw bead would. But here's the part sprung back without the bead, and here it is with the bead in a much more controlled state. Here's how it actually works. We close the part, the U channel's forming. Here we can see the stringer bead clamping, and then we do some post stretching. There's a lot of timing required in getting this die right, but it's a wonderful way of, if you have the ability to do this complexity of die, to get the U channel formed, pin down the stringer beads, and then do some post stretching of the part. Should get you your shapes that you're looking for. Another new method we're doing with Gen 2, Gen 3 steels is the active binder force control. And here you can put a variable binder force on of medium, low to high. And here you can see a constant binder force gave you the part with the red arrow. The variable binder force from low to high gave you the one in the middle. But this one in the bottom, which showed a lot more control, was medium, low, high, and was able to produce much better. Full details on this can be picked up from Dr. Danny Schaeffler's site at Engineering Quality Solutions. The key points to summarize, because I'm at my time for theory here. Let me just summarize some of the key points. Open wall angles achieved with minimized metal flow over die radii minimize the angular change and sidewall curl. Overbending accounts for angular change. It allows the part to spring back to the targeted dimensions. Note that this approach is less successful in addressing sidewall curl. Applying in-plane tension to the sidewalls after forming reduces spring back. This method includes stake beads, hybrid beads, and active binder force control, some of those more advanced issues that I was showing there at the end. With higher strength steels, it is still difficult to achieve sufficient stretch to this sidewall by simply increasing the blank holding force. Preventing the metal flow into the wall during post-stretching may require lock beads. Bead geometry affects blank size and press requirements. So if you are going to go to lock beads and a different type of, or even double lock beads, you're adding a lot to the blank size and you're raising the cost of the component and of the die for your customer. The best way to handle all this spring back is to cut it off right at the OEM or your supplier and ask for geometric stiffeners like darts, beads, or flanges to lock in those elastic stresses to prevent spring back from occurring in the first place. All the forming, trimming operations you do after the fact will relieve those stresses, resulting in the dimensional distortion. So in addition to that, you often have to increase the press requirements to have more load and energy to form those features, especially with the dual phase or ultra high strength steels. In summary, design the part and tool in such a way that spring back is desensitized to various material, gauge, tools, and forming processes. I think Cimatron's going to really help you there, given that it's a full parametric hybrid design system changes can be made very easily. And that affects the effects of springback are minimized rather than attempting to compensate for it. The accuracy of the forming simulation programs to depict springback continues to improve. It's not perfect. And so whether you're using a one-step incremental A, incremental B, or incremental C to calculate your springback, understand where their data sources are, whether they've got the complete material characterization, what model they're choosing to do their analysis with, and what the changes are to the specific forming method. Challenges. Even without full accuracy, springback simulations can predict the trend. So even if you're not getting the best accuracy, at least they show you the trend that you're dealing with, and they can test the effectiveness of all the countermeasures you're going to throw at it. Again, having a fully parametric design system to allow you to implement these countermeasures and quickly get feedback will tell you how you can control your springback, how effective you'll be in controlling your springback. In all cases, don't believe the computer. Verify your predictions against physical measurements. If we look at the die compensation procedure, we're going to start with understand your material properties. Have a robust die design. Look at your forming simulation to understand whether your part forms properly or not. Make sure you're within the proper threshold for thinning, for wrinkling, and that you've achieved the required strains in the part where necessary. Perform your springback analysis. Even doing this early would help you in tolerance negotiations when you're in the quoting and estimating stage. It's an important aspect because you'll get a very early indication of where you're going to have springback issues. So you should allow extra stations to compensate for it and extra costs in your quotes to deal with that, your estimates to deal with that. You need to get an accurate deformed cloud points back, compare it to nominal, and then have stellar morphing technology to imprint those new compensated data into your designs. Again, you're going to be in this iteration loop several times until you get it right. Take your compensated data, run it back into your die design, check your forming simulation, check your springback analysis, create your deformed points, compare nominal and compensated, and see where you end up. Understand your material properties, high quality, parametric hybrid die design, get your forming simulation locked down, check your GD&T to see where your tolerances are and where you need to hold your springback, compensate with your deformed points and apply the right compensation percentages and values, and make sure you've got advanced morphing technology to imprint that new knowledge into the design. If we take a look at here, after we get through thickness and safety, we can run a springback analysis on a design. This is now a screenshot within Cimatron. We get a mapping of the magnitude, the color plot. You can see the top surface in blue is going to be near 0. And as we get out near towards the wings on these flanges, we're starting to see as much as 0.477 millimeters deflection. There's the springback. If we now take a look at the red is the springback and the green is the nominal part, you see the separation on the two flanges. Now we can take that data and say, let's go grab the springback data and let's deform the part. There's our nominal part, and we're going to keep the original. We've identified the tip direction in here. And now we're going to look at the point cloud. Here we have almost 5,400 points in our cloud, an adjustable factor here, 1.15, so 15% compensation. And we not only get the nominal, the deformed points, but we get the target points for the deformed mesh at a 1.15 factor. Now we imprint that against the part. And when we imprint that, when we imprint that against the part, we can now go ahead and see that we get the part data from the customer, which is the nominal, the springback data, which is the STL model, and we end up with the data that we compensated at 115%, or the compensated model. That's going to be the method we're going to go through. So before I jump to it, let me introduce David Lindeman, our Senior Application Engineer, to take you through a demonstration. David?
Okay, thank you, Dan. So we're going to move along to the tool. Of course, we talked about using this in the quote process to understand what we're doing with the material. But here we're in process. We've got a die set laid out, and we've got our strip already laid out. So we're going to move up on the strip, and this is going to help me see where I want to address the springback issue. And right here where we go from the blank to our first form, this is where we'd see quite a bit of the springback, and we'll go through the analysis of it to make sure that we have what we need. So in the process of this, we're going to create what we call cutting sheets, which is the purple. Basically, it's on the die side of the material, so this will be the die side cutting sheet. It's what we would use then to cut the tops off basically of all our die steels. Using our blank function, we're going to be able to do our calculations for the wrinkling, the thinning, and also the springback. Under material type, you saw a type of material that was listed, so there's an extensive library of different materials already in the system, and we're just going to have it go ahead now and do the calculation for the springback. So this takes a second or two. We're assuming no conditions on this where we're trying to hold it or anything like that. This is just a quick look at what we might see for springback. Over in the red, you see there's as much as more like 2 millimeters in the magnitude, showing us how much that's going to spring back. We can look at the percentage of thickening and thinning, and also our safety zones, which are going to highlight the areas where it could likely wrinkle. We've got the information, so now we're going to save this into a CSV file. That basically is going to help us to calculate our vectors, so we know how much each area has moved. Go ahead and let that run, and then we'll get exactly the sheet that we need that we would use then to cut the top of the die steels. Now, as we said, this is an important thing to have in quoting, perhaps looking at the part like that example Dan just showed you. But here in tool making, it's also critical. I want to apply this to the tool and leave the strip itself as nominal. So taking the information we have now, we're going to go into our warping utilities here. We can keep the original, that way we can see what has been warped as compared to what nominal would look like. And we'll pull in that CSV file now that we just created. This is basically a one-hit look at what could happen with our springback. Those little vectors you see in white are showing you the movement of the material. We could go ahead and calculate that. We want to calculate it opposite side. So instead of warping it further away, we warp in the opposite direction. And those little arrows there, or little light bulbs that I just clicked on, help me see what's happening. So I got the white vector direction coming off that yellow dot, purple dots in the opposite direction. So I know for sure that I am doing the opposite, or I'm compensating for that springback. Scale factor would allow me to apply a percentage of that overall compensation. So maybe I don't want to go 100%. Maybe I want to creep up on it and take a couple shots at it. Or like Dan said, you're going to go ahead and do your compensation, then take it back into your simulation to see that it is working like it should. You've got the percentages to where you need them. Quick zoom up, you could see in that corner that there was definitely the difference. Here's what the simulation looks like from Inspire form. Here you see the first hit showing us the percentages. Now we're looking at different zones. You can see it's just simply the punch coming down on the die. And here you see the plot showing you the amount of deformations. So with that done, our first look, we can go further now and see this in another light. So here I've got my surfaces. I'm going to go through the same process again. this time I'm going to have a little bit different of a file, and we'll talk about the differences here. Again, I'll go into my warping utility, and I'm going to grab a point cloud, basically. Now, this is coming from a different approach. This is what we would call an incremental. So here you see the arrows. Again, the vectors are showing me the directions. As Dan said earlier, there are different types of simulation, a one-step, incremental. Same process, though, where we're applying the opposite side, looking at those vectors and seeing that we've got a compensation. Right there you can see the purple dot quite a bit better than the first one. So we know we're compensating in the correct direction. We'll say okay, and it does all that. The amount of work it does in a short amount of time is really impressive. And there's some definite controls that you have in the software. Maybe there's an area where I don't want to do 100% or 80%. I can window in an area and say, give me just 70% in this area, but 120 in another area. It's really up to what you see that you need, and you can use that tool to compensate. Here with the incremental, you can see that we're bringing the pads and forms down on top of the die. And you can see the results both with the wrinkling tendencies, also the plot showing us the deformed areas or how much those points are going to move. All right, with that done, we've looked at the two simulation types we could use. Let's go back into our tool. Of course, Cimatron is software meant for tool design as well. And here we've got a already started die set. I've got some die and punch forms already in place. Now we need to get that compensated surface on it for the spring back. Basically now I'm taking the form and I'm using that cut sheet to cut back the block I drew. And I'll do that with other forms here just so you get the example of what it would look like with inserts, maybe some retainers around it, things like that. You notice too that there are different types of components, screws and dowels. All that comes with the system. It's got an extensive library of different die components that you would use. Once you place it, it automatically places the hole, keeps track of how many times you've used it, so on. So here you can see very quickly we can just simply cut it back, and we'll have the die forms that match the compensation that we need. Now with that, we talk about changes that might occur. Here we did it at 100%, which would be aggressive for the first time and looking at it. Again, in reality, we would take what we did with those cut sheets and we would take it back into our simulation and compare that and do that again and again. It might have a bit of an iteration doing it several times, but it's important that we find out here rather than find out when we cut the steel. It saves us a lot of time and money. That's the whole purpose behind it, of course. So we can do that. Maybe we'll go back into the original part here where I've got that cut sheet. Everything is parametric, so I go right back to where I did that warping, and we'll hop over to our morphing tool where I've got my points and change the scale factor for maybe I want 3/4 of what I'm going to use here. So I'm holding back 100%. Recalculate the points. It gives me the vectors, the correct vectors now. And here we just go ahead and say, go ahead and do it. If I'm confident, maybe I don't want to keep that second face, keep get rid of the original so that all I have now is the compensated face. That way I'm working with just what I'm going to cut with. Once that's done, here you see everything will update. That cut updates based upon the cut sheet being different, being warped differently. So you can see you can do it on the part. You can use the part data to get that analysis that you need, or you can use it here on your different forms. The cut sheet method is preferred. It's a single sheet, and you know exactly the areas of that die that you're affecting. So taking this forward, one might ask, well, what about the punch side now? Same process, if you so desire, using a punch cut sheet, or I could simply make one. If I've got that deviation in there I need for the or the compensation I need, then just a matter of offsetting this to get the opposite side of tooling. So here we're going to do the offset. We'll go the part thickness, make sure we offset in the correct direction, and let it give us that punch cut sheet. One nice thing is you can preview it, make sure you get everything you want. This particular function's not an all or nothing function. You can get complete results, partial results. Maybe there's one little tiny area that would be affected. Well, you can get the rest of that area and then do what you need to do to fix that tiny area. Here I've got the offset punch sheet. I'm picking my punch block, and from there, let's say pick that punch sheet. Now I've cut it back to get the opposite side of the tool. So fairly quickly we've incorporated it. You've seen how we can apply the compensation for spring back and then apply it to the tool. And the nice thing is if I go back and change that percentage I'm applying it by, I can continue on, update it, and I can be confident that the tool will be updated to that amount of percentage.
Fantastic.
Yeah.
Thanks, David. So let me bring the team back in. Ralph, you're with us?
Yes, I am.
Mason, you're with us as well?
Yep, I'm here.
Great. So a couple questions have come in, and we'll just throw it out to the panel. The first one is, does the software have any material data sheets? Mason, do you want to take that one?
Yeah, sure. The software does come with many data sheets that's already included in the software, but it is highly recommended that you do your own testing. Those data are there for reference. They're close enough. You can get your job done, but it's highly recommended you test your material to get, and sometimes you might find them to be really accurate, to be right on. It depends when they updated this data sheet, but that's the direction.
Mason, when you were working in the industry, how long did it take you from when you sent out a coupon of material till you got test results back?
Oh, it's in a day. It's the same day. You know, you send it out, you get the material tested back, you get it. You know, we used to send it to a local, to Tyson Krupp. They give us all that information. Then you take that information, you plug it into Cimatron, you verify it against their document, and then once you have that confidence level, you move on pretty fast with it, and then you feel comfortable of what you're getting done. And I think that's the goal, is to get you comfortable and the confidence level to be up there.
Now, I know it was a few years ago, but what did it cost every time you sent a coupon to the lab?
It wasn't like $100 or about 100, 150. It depends, you know. It wasn't that much for the materials that we were testing or we were doing at the time. We were doing aerospace, so we couldn't, test 300 parts and see, it was very expensive. So we want to make sure that our blanks and our information is accurate, because we didn't have that much, room to, let's throw another 100 parts. We didn't have that room. So things had to be perfect or near perfect. And we were able, actually, we got really great results from that. And that's a few years back.
Yeah, but understanding that you were working with Hastelloy and Hastelloy X and Inconels, that's pretty exotic material. So a couple $100 was well worth the while to get accurate material properties.
Absolutely, yes. Spend the money. It's well worth it. Saves you time, saves you cutting, welding. That's the last thing you want to do, is weld on the shop floor and then recut and re-weld and recut. That takes time and that cost. And every time you do that, you're just slowing down. You don't want to do that. You want to do it at the front stage. You want, as an engineer, figure out all these information and plug it in. And once you have that done, and to be honest with you, we were really successful as how many times we had to cut and recut. If I say the numbers, people are going to laugh, but I really don't want to say it. But once you do it, you'll be really impressed how well you get your job done faster.
Excellent. So as a follow-up, what are the Gen 2 and Gen 3 steels? And maybe I'll just tackle that one myself here. So we'll start off with first generation advanced high strength steels. They're based on a certain chemistry. For those of you that are chemistry majors, it's based on a ferrite matrix for a baseline ductility with varying amounts of other microstructure components like martensite, bainite, and retained austenite to provide strength and additional ductility. These have enhanced global formability compared to conventional high-strength steels at the same strength level, but there are some local formability challenges that arise due to the wide hardness differences in the different microstructural components. I'll also say that a material in North America, a material in Europe, and a material in Japan or China is quite different, even though they would call them the same material. They are produced differently. A Gen 2 or second generation advanced high strength steel starts to get into an austenitic microstructure or twinning deformation for extra strength and ductility. The austenitic stainless steels have similar characteristics. They're sometimes grouped in this category as well. These are typically higher cost grades due to the complex mill processing that the steel mills provide to produce them, as well as highly alloyed, of the latter of which leads to welding challenges. Here you're going to find a lot of your dual phase and higher strength steels. When you get to the Gen 3, that's an advanced high strength steel that starts to enter into the multi-phase category. And this is a highly engineered material for enhanced formability. It's measured in tensile, sheared edge, and bending tests. Typically, these steels rely on retained austenite in a bainite or martensitic matrix, and potentially some amount of ferrite or precipitates. They're highly advanced, and to get more information on first gen, Gen 2, Gen 3 steels, I highly recommend you go back to the references I listed earlier, to the Automotive Steel Partnership or to the World Auto Steel Group, and attend some of their free lectures on understanding the material properties a little better. Third question, why do we have to run a formability simulation first before we get the spring back analysis? Again, maybe I'll jump on that one because it's part of the theory. When we run a formability analysis first, we're understanding the strains that the punch and the die and all the rest of the mechanisms like binders and blank holders and pressure pads put into the part. So all those strains are induced in the part, and then when that part holds its shape, that's when all those strains are induced. Spring back is when we let go and release that part from the die, and it wants to spring back to a degree to where it feels more comfortable. So unless you understand the strains you put in from the formability analysis, you can't run the spring back analysis to then release those strains to understand where the part will spring back to. Fourth question, once I apply the spring back, can I change it later? David, do you want to tackle that one?
Sure. Yeah, absolutely. You can change it. I tried to illustrate that a bit when we went through the demonstration, but there may be situations too where you'll have to change it. So it's just a matter of going back in the function, applying a different percentage, or you can window an area in where you see there's more involved. You know, pick that grouping of points and then change just the percentage in that area. So it's very, very flexible, and you can do a lot of nice things with it. The function itself also allows you to manually manipulate your data. We can take points from CMM and use those. So maybe you've made the die, you see there's spring back on the part, you take your points, now you can go back and put those points in and use that to manipulate that sheet or the top surfaces of your tooling. So it's very flexible. It's a powerful tool. What one guy say, I got this corner, he measures it, it's up a quarter of an inch. You can go in there and manually manipulate it and do whatever he has to do just to make that compensation. So it works across the board in all kinds of different ways.
Next one I think goes to you, Ralph. It's is the springback function an extra cost? And here I think they're talking about the springback function inside of Cimatron. Ralph, you're on mute. Mason, let me throw that over to you then. Oh, there you go, Ralph.
Yeah, sorry about that. The springback calculation inside Cimatron, that's an FEA-based calculation. It takes into consideration the material properties and everything like that. We do have a bundle, a die design bundle that has every module in it. But those that are just doing like the estimating and want to look at that, it is an add-on to the base CAD module. And I think it's around 6K for that add-on module, but it's very, very powerful. So the other thing that I want to mention too, when we look at these compensated models, we're taking the original part, we're comparing it to an STL model, then we're compensating it in the opposite direction, but we're keeping that as a full CAD model. It's not an STL model. So it's kind of unique for softwares to do that. And I don't know if we're the only ones, but we keep it as the CAD model.
So the STL is only affecting those surfaces. You still end up with your Class A or advanced surfaces that are deformed and they're smooth. They're not a mesh. They're not mesh. They're true surfaces.
True. And whether you do it manually, and like Dave said, drop this end down a quarter, it's still keeping it as a true surface model.
And that new deformed surface was used then to cut the solids for the blocks to create the punch and the die and the pads, etc.
Yep, exactly. Yep. Yeah, because we all had experience with STL models and cutting a block and then ending up with an STL block and how fun that is, right?
Yeah. Final question here, Mason. I think I'll go to you for this one. What's your experience with the number of compensation iterations you need in the software to control springback?
Oh, wow. You brought back memories. Well, the very first time I got introduced to it, and I was kind of, reluctant and hesitant. I didn't know how accurate this was. And it took me about 7 to 9 times to get this iteration going. But then once you understand your material and you understand which way it's behaving, that gets down very fast. And it actually got down to 3. So basically you do 1 in a median, as your example you showed, and then 1 top, 1 bottom, 15 up, 15 down. And then you run it again and you see it. And realistically speaking, by the 3rd time, you have an answer. But at the beginning stage, yeah, you take a few just to understand it, which direction it's going. And then once you have that, we did aerospace parts and we had maybe 4 or 5 major materials. So we saved everything the way it was. And then once we figured out what it was downhill from there. But if you have a lot of different materials, then you just got to go through the pains of understanding. But it does go a lot shorter.
So the more you work, the more work you do with a material, the better you understand it, and the shorter your compensation loops are going forward.
Right. It's exactly what you just showed earlier. Your FEA analysis and all these points, and brought back memories. You really have to understand that. Once you understand that, things become much easier.
So amazing. You're talking about doing a simulation and maybe only doing it at 80%, and then taking those results and redoing the simulation. You're not actually cutting the tool 8, 9 times in the beginning, right?
Yeah, no. That's what we used to do. And we ended up, so I'm going to give you the answer. We only cut once. After running the product, you only cut once. We were so successful that it was just impressive that we never had to recut the tool again, because we knew where the numbers were. We knew what the springback was. We knew exactly where everything was going. And there's another thing here that I think, Dan, we didn't talk about is material expiration. And we found that out the hard way. Pay attention to material expiration. There's a date on the material. And it is true, material does expire. If you have for a long time and it says it's expired, don't think that's going to behave correctly. So make sure your material is correct.
Excellent. We'll wrap it up at that. We're at the top of the hour. I thank everyone for attending. Look forward to our next in the series of die webinars, and soon to be introduced some mold webinars. There is a QR code on the screen. We invite you to Cimatron.com to see this. This webinar will be posted there in a couple of days. You can always review the contents of it there. And as usual, if you want to reach out to anyone on the team, just click the QR code and we'll get right back to you as soon as possible. Thank you for sitting through here and listening to it. And thank you, everyone, for listening to my lecture. I don't get a chance to lecture like that often, but hopefully everybody stayed awake. Thank you for attending. Take care. Have a good day now.
All right, thank you.
All right. Bye-bye.
Bye.